Simulation to investigate what affects wave speed. So I started the simulation. I think I've got the amplitude set to 0.75 centimeters, the frequency set to 1.5 hertz or 1.5 cycles per second. Now mind you, I've got it on slow motion. This is normal speed, so clearly this is going around 1.5 times every second. And this is going up and down 1.5 times every second. I'm going to put it on slow motion because it's going to be a lot easier for me to see and watch these waves traveling, because wave velocity is how fast the wave gets from the beginning over, and out the window, say. Remember, velocity is distance divided by time. So we're going to want to take note of a certain distance. I'm going to choose 5 centimeters. And I'm going to use the stopwatch, which I've turned on, or the timer, which I've turned on. And I'm going to use the rulers, which I've turned on, to measure 5 centimeters. So I'll get the time it takes the wave to go 5 centimeters. I've got it on oscillate. I've got it on no end, so the waves are going on forever out the window. I've turned off damping completely. Tension is still high. So I'm going to measure the wave speed of this wave right now by watching when this gets to the top. I'm going to track the wave over, and I'm going to stop it at 5 centimeters. So here we go. Start. Watching the wave travel, bang. 0.82 centimeters, or 82 seconds. Take another measurement, check my time. Start. Travel. Stop. 0.81 seconds. One more time. Bang. Stop. 0.81 seconds. So it's taken about 0.81 seconds to go 5 centimeters. So remember, 5 centimeters is 0.05 meters. We like to talk about things having a velocity in meters per second. So 0.05 meters divided by per 0.81 seconds. So I'm getting a wave speed of about 0.06 meters per second, or about 6 centimeters a second. So I'm going to keep that in mind. 6 centimeters a second, 0.06 meters per second. I'm going to change the frequency. I'm going to cut the frequency down to a nice significant difference from 1.5 down to 0.5. Run this thing. So it's going to be a little harder to track because the peak is kind of flat, but we should be able to do it. Doing the same thing, watching this very flat peak travel to 5. So I'm going to go, watching it travel, stop. 0.8 seconds. One more time, go, and stop. 0.82 seconds. It looks very much the same as before. Go, stop. 0.81 seconds. I'm going to say this is traveling at the same speed because it took the same amount of time to go the same distance. So about 0.06 meters per second again. So frequency doesn't seem to be having any impact on the wave velocity. I'm going to come back up to 1.5 hertz, or 1.5 cycles per second. I'm going to change the amplitude. I'm going to just crank it all the way up. Why not? That'll be an easier peak for me to measure. Move my ruler to match what I've done. Keep 0 right at the beginning. There we go. All right, and same deal. I'm going to wait for this wheel to get to the top. And go. Following it. Stop. 0.77. And go. Following it. Stop. 0.8. One more time. Go. Stop. 0.77. Well, I think I might be anticipating things a little bit. I've changed the amplitude significantly, and I'm getting a very small difference in the time it takes to go 5 centimeters. I'm going to try one more time. Little tiny bit faster. I think that's me, not the machine, or not the wave. So I do not think that amplitude has any effect. Let's try a very small wave, how about? Say, let's do 0.25. Can I even see that wave? Bring my ruler down. That should work. All right, so go and stop. 0.8. Go and stop. 0.81. Go. Stop. 0.82. So going from an amplitude of 0.24, 0.25 centimeters to an amplitude of, what was it, 1.25 centimeters had virtually no distinction, no effect on the wave velocity. So we've determined that frequency doesn't affect the velocity and amplitude doesn't affect the velocity. Something's got to affect the velocity, right? So I'm going to get my amplitude back to 0.75. I'm going to move my ruler up to the right place there. And I'm going to change the tension. Now notice the wave has gotten a little bit shorter wavelength. Now same deal, I'm going to start it, follow that wave along, and stop it. 1.33. Now that's a significant difference in the velocity, or in the time it took. Go. And stop. 1.33 again. Go. And stop. 1.29. So it's about 1.33, 1.32, 0.05 divided by 1.32. So I had a velocity of a little over 6 centimeters per second. Now I've got a velocity a little under 4 centimeters, 0.0378 or 3.78, 3.79 centimeters per second. All right, one more thing. I'm going to go to a low tension. I get this very short wavelength now. And go. Whoops, did not do that right. I paused it. All right, go. This one's a little harder to follow. Hope I haven't lost track of it. It's moving so slowly that it's easy to lose track of. And it's certainly taking its time getting to 5 centimeters. Stop. 4 seconds. Do another one. Watch it carefully go. All right, 1 second, or 1 centimeter, 2 centimeters. The most boring race ever. 3, 4, and 5. About 4 seconds to go 5 centimeters. So I'm going to do 0.05 divided by 4. So we're going a little over 1 centimeter per second, 1.25 centimeters per second. So we found amplitude not affect wave speed. Frequency does not affect wave speed. Tension, however, does affect wave speed. Low tension, slow waves. High tension, fast waves. All right, so that is wave speed and the things that affect it, or the thing that affects it.